Stanford University.
All right, what I wanted to talk about before going into Maxwell's equations, we've talked about the motion of a charged particle in an electromagnetic field. We have not talked about the dynamics of the electric and magnetic field, in other words, the field equations, or for that matter, the related effect of charges on the electromagnetic field. We're going to do a bit of that tonight. This time, not starting with the action principle. I'll tell you why. We'll come back to the action principle, but first I thought we sort of jumped to some very formal and mathematical technology. I had occasion last week, actually while I was in Belgium, visiting Mrs. Solvay of the Solvay family, who were the people who first brought together probably the very first physics conferences that took place ever in the early 1900s. I had occasion to look at Einstein's first paper. I had to struggle through some of it in German, just because some historical discussion came up about, and I looked at it and I read the first basic paragraph. The title of the paper in English is On the Electrodynamics of Moving Objects. And Einstein expresses, I had read this long ago, in fact more than once, and I'd more or less forgotten about it. He expresses extremely clearly what his logic and what his motivation is. And I'd like to come back to it and just discuss it for a moment because it is deeply connected with the transformation properties of the electromagnetic field tensor. I want to go through it. If you have access to Einstein's first paper, it's worth, first of all, it's worth reading. You can now, I'm sure you can understand it now. But if nothing else, just reading that first paragraph is, it's marvelous. I wish I had it here. I would read you the first paragraph, but I don't. But he expresses the puzzle, which by that time no longer puzzled him, but the puzzle of the invariance of certain electromagnetic phenomena that in fact you describe in different ways in different reference frames. In one reference frame you blame a certain effect on a magnetic field. In another reference frame you blame it on an electric field. And he says, look, there's no real difference between the phenomena viewed in the two frames, but we describe them in a completely different way. There's something there that we should understand the transformation from one frame to another and why two different descriptions give rise to exactly the same phenomena. In other words, he's talking about relativity. And the two phenomena he's talking about, or the single phenomena he's talking about, is of course the effect of electromagnetic fields on moving and stationary charges. More explicitly, he talks about charges moving in wires, in other words, currents. It doesn't matter very much whether the charges are moving in wires or whether they're just moving in free space. He might have talked about charged particles moving in space, just ordinary charged particles. The reason he didn't was probably because at that time it was not easy to see the motion of a charged particle. It was much easier to push a particle through a wire, charged particle through a wire. But in any case, here was the situation he was talking about. Here's your three dimensions of space. Let's suppose that there, what can we call them? We can call them x. Let's see, x, y, and z. I guess this would be y, and this would be z. And supposing, I think I have in my notes here that I called this y, which is probably inconsistent with the right-hand rule, but never mind. X, y, z. And let there be a magnetic field pointing out of the blackboard, in other words, By. A magnetic field, and that's the only component of the electromagnetic field. What would create such a magnetic field? Well, it could be the poles of a magnet. The two poles of a magnet, a pole over here and another pole over here with a magnetic field into the blackboard. Let's see, North Pole, South Pole, magnetic field coming. I know that doesn't look like it's coming out of the blackboard, but think of it as out of the blackboard. In other words, along the direction y. And let there also be a charged particle, and the charged particle is moving along the x-axis. It's moving along the x-axis in this direction. In our frame of reference, all there is the magnetic field, and the particle is moving. All right. Now, in Einstein's imagination, he really was thinking about a wire in this direction. The wire contains, of course, we know what the wire contains. The wire contains atoms, and the atoms are nailed in place in the wire. They can't move. And electrons. And electrons in a conducting wire can move up and down. So really, it was only the electrons that mattered. Einstein didn't talk about electrons and protons and neutrons and so forth. He just talked about a current in a wire. But he might have been just talking about a charged particle. And now the wire is made, the wire or the charged particle is made to move along the x-axis. What happens? What happens is a force is exerted on the charged particle. We call it, and in fact Lorentz, I don't know what Lorentz called it, but Lorentz knew about it. It was the Lorentz force, V cross B. Electric charge times V cross the magnetic field. So if the magnetic field is out of the blackboard, the particle is being forced to move along the x-axis. There will be a force which is both perpendicular to the velocity and the magnetic field. The magnetic field is out. Velocity is this way. So there's a force on the charged particle, either up or down. You're a better man than I am if you can figure out instantly which way it is, whether it's up or down, and I don't care for the moment. Yeah, you're right. Is it down? Well, that depends on whether the charge is plus or minus. Okay. Right, okay. But there's a charge there's a force along the y-axis, which, for example, would cause a current to flow along the wire. That's a description from one frame of reference in which the effect on the charges, the current is produced by the motion of a charge in a magnetic field. Now, Einstein then says, wait a second, we also know another fact. This time, keep the wire fixed, don't move the wire, but move the magnet. Move the magnet, and what happens when you move a magnet and you have a wire like that? Well, according to Einstein and everybody else at the time, a moving magnetic field like that will create what they called an EMF, an electromagnetic force, which effectively means an electric field. It creates an electric field, taking a magnetic field which points either into or out of the blackboard, and moving the magnet creates an electric field vertically, which has the same effect, causes charges to flow, or exerts a force on a stationary particle. Imagine now, in other words, if there were a stationary particle but a moving magnet, it would have the same effect. So what Einstein said is, look, we have these, the phenomena is the same. A vertical force. We have two totally different descriptions. In one description, the magnetic field exerts a force on a moving charge, and the other, the moving magnet creates an electric field, and the electric field exerts the force on the charged particle. His attitude was, these are the same effect. These must be the same effect. And the only explanation is what looks like a magnetic field, a pure magnetic field in one frame of reference, in another frame of reference, namely in this case the frame of reference that happens to be moving with a particle, looks like a bit, at least a bit of electric field. So what he said is electric and magnetic fields are part of the same complex of objects which transform into each other under he didn't call them Lorentz transformations. He probably would have preferred that they were called Einstein transformations. I don't know. But motion. Okay, so can we see in detail, mathematically, this transformation when, if we have a magnetic field, let's forget the charged particle now, we have a magnetic field. In your frame of reference, there's a magnetic field pointing at it, and that's all, just a magnetic field. And I move along with the charged particle. Can we see that I perceive an electric field? Can we see it from the transformation properties of the electromagnetic field tensor? Okay, so for that, we need to explore a little bit the transformation properties of the electromagnetic field tensor. We did some of this. I want to come back to it and talk about this particular effect. All right, let's remember what the electromagnetic field tensor is first of all. It's a thing with two indices, F mu nu. It happens, just to put everything out on the table, F mu nu happens to be expressed in terms of the vector potential. Let's write it, although I don't think I'll use it for the moment. D mu A nu minus D nu A mu. This means the derivative with respect to x mu of the nth component of the vector potential minus the derivative with respect to x nu of the muth component. D sub mu means d by dx mu. All right, that's the field tensor. It's antisymmetric. Just to recall a couple of facts about it. Mu and nu go from 1 to 4. They run from time, x, y, and z. Time is 0. X, y, and z are 1, 2, and 3. And F naught n, that's the time, that's the mixed space-time components. Oh, incidentally, this is antisymmetric, and so the diagonal elements of this are 0. But the mixed space-time components are electric fields. Little m and n now are ordinary spatial components. Mu and nu are space-time, m and n are space. All right, so that's the connection between the field tensor, antisymmetric field tensor, and the electric field. It happens from this equation here that it's the time derivative of am minus the, no, sorry, this is n. If the left-hand side has an n, the right-hand side has to have an n, and times the time derivative of, no, sorry, times the n derivative of a naught. All right, that's just rewriting this for the naught. All right, I'm not going to use this particularly, the expression in terms of the vector potential, but just to remind you, that's the electric field, and the magnetic field is related to the space components, mn, and the connection is that the magnetic field is equal to the curl of the vector potential. When restricted to the space components, this expression here is simply the components of the curl of a vector. And so the corresponding, the Fmn, the magnetic field is the curl of the space components of the vector potential. For example, this would say, for example, an example of it would be that b sub x is equal to the derivative with respect to y of the z component of the vector potential minus the derivative with respect to z of the y component of the vector potential. This is just shorthand for these equations, 3 of them for bx, by, and bz. Okay. Now we can summarize the connection between the electric magnetic field and the field tensor by writing down a big matrix, a 4 by 4 matrix, and filling in the components with electric and magnetic fields. So just to write that out once. I know we've done it before, but let's do it anyway. F mu nu. There's a big matrix, and in order to keep track of the elements, we will let nu run horizontally and mu run vertically. That's a standard rule. The second element here runs horizontally. The first element runs vertically. And the first, we can, just to organize the matrix, let's put some guidelines in. It's a 4 by 4 matrix. All right. The diagonal elements are 0. In the upper right-hand corner here, just to remind you, the first row here is the time component. The next one is x, y, and z. And likewise for the rows, time component, x, y, and z. The mixed space-time components are electric fields, so that means along here we have electric fields, Ex, Ey, and Ez. Minus Ex, it's antisymmetric, minus Ey, and minus Ez. And then the other components, the space-space components, are components of the magnetic field, and those get filled in as the y component. No, that's the z component. Whoops, sorry, z component. Why is it the z component? Because it is the xy component of f. Xy component means the z component of b. You'll just have to remember that. Minus b sub y and b sub x. And down here, minus bz. That's the antisymmetry. What's in the lower half of the matrix is simply the reflection, except with a minus sign, plus b sub y and minus b sub x. And that's the electromagnetic field tensor. Incidentally, just to, let's see, if I put, here's a little exercise, fill in the blanks for f mu nu with upper indices. The rule is whenever you go from a lower index to an upper index, if you have raised a time component, you get a minus sign. If you've raised a space component, no minus sign. All right, so in fact, it's easy to work out what f mu nu with upper components is. It's in fact exactly the same, except one slight difference. Let's see here. We need some lines in here. The only difference is that this is minus Ex, minus Ey, minus Ez, Ex, Ey, and Ez. Why did that happen? That happened because the electric component has one time index and one space index. So when you raise the indices, you're raising one time component and one space component, and that gives you a minus sign. The magnetic terms are the same, are unchanged. Bz minus By and Bx, and you can fill in the lower corner here. It's just antisymmetric. All right, so that's, it doesn't matter which one of these you use. You fill in the blanks, and that's the field tensor.
I'm reading this correctly. The magnetic components don't have any time component?
Yeah, the magnetic components are space components, pure space. So that means, okay, where are the space? Let's take advantage of some colored pens and block out here the space components. This is time, x, y, z. All right, so this green 3 by 3 matrix is the space components. And they consist only of magnetic fields and zeros. The mixed space-time components are the ones along the edges here. Okay. Now, what do we want to do? We want to figure out how this object transforms when we move from one frame of reference to another. In other words, given an electromagnetic field tensor in one frame of reference, in which the electric and magnetic fields are what are written down here. If I now move relative to it, and let's say move along the x-axis for simplicity, if I move along the x-axis, what are the new components of the electromagnetic field tensor in the new frame? All right, so to work those out, we simply have to remember the rules for transformation of tensors, of things with indices. Tensors are just things with indices. All right? So let me go back first to the simplest of all. Well, the simplest of all tensors are, of course, scalars, and scalars don't transform. They're too simple. But 4 vectors. In particular, the 4-vector x mu prime. It's x, y, z, and t, or t, x, y, and z. We know how they transform. In fact, they transform by Lorentz transformation. T prime is equal to t minus vx over square root of 1 minus v squared. X prime is equal to x minus vt over square root of 1 minus v squared. Y prime equals y. Z prime equals z. But we can organize this into a matrix expression. Well, we can write it in 2 ways. We can write it using the Einstein summation convention. We introduce a matrix called L for Lorentz, mu, nu, x nu. Now remember, we sum over nu. This is shorthand for the set of 4 equations here, summing over nu. And if we do that, we can read off the component, or we could, another way to think about it, same equation, is to line up x prime, this is x1, x2, x3, x4, no, sorry, x0, x1, x2, x3, and prime the whole thing. I don't want to put the primes in here. There's too many. That'll make it look like it's x11 or x21 or x23. I don't want to do that. Just prime on the outside. And that's given by some matrix L, a 4 by 4 matrix, whose components are called mu nu, times the column vector x0, x1, x2, x3. Same equation. And the matrix L, can we read off the matrix L? Sure, we can read off the matrix L. We can read off the matrix L from this equation here. I'll write it down for you. The matrix L that's associated with the Lorentz transformation is again a 4 by 4 matrix. I put lines in so that just to guide my eye. I'm not very good at keeping rows and columns neat, so I put the lines in. All right, so x naught prime is a 1 over square root of 1 minus v squared here. There's a 1 over square root of 1 minus v squared here. There's a v over square root of 1 minus v squared. Also here, v over square root of 1 minus v squared. 0, 0, 0, 0, 0, 0, 0, 0, 1, 1. Ah. Sorry, I didn't hear what you said, but I suspect you said there was a minus sign here. Is that what you said? Yes. Thank you. And it's correct, of course. The minus sign is this one over here. And now we have it. If this matrix is multiplied by x0, x1, x2, x3, also aka t, x, y, and z, aka stands for also known as, t, x, y, and z, it simply reproduces these four equations over here. So this is the matrix which represents the Lorentz transformation by velocity v along the x-axis. All right, now what do we do with a tensor like f mu nu? How do we transform it? I will take the tensor with the upper version of it. Why? Just because I already have rules for things with upper indices. I've written them down there. How do you transform a thing with 2 upper indices? Here we know how to transform a thing with 1 upper index. Here's the transformation for a thing with one upper index. In fact, you know what I'm going to do? I'm going to change this index here. I'm going to call it sigma. Sigma. It's a summation index, and so it doesn't matter what I call it. I'll call it sigma. All right, so let me write down for you, and it's more or less obvious what to do. You write down that f mu nu prime, the field tensor in the new coordinates, in other words, in the moving reference frame, is L mu sigma, exactly that same object that's up on the top of the blackboard. That's how the mu index, that's associated with the transformation of the mu index. The transformation of the new index is you put another L, this time, and introduce another summation index. What do you multiply it by? You multiply it by f sigma tau. In other words, the way the mu index transforms is exactly the way it would if there was only the mu index, L mu sigma, F sigma. The way that nu index transforms is exactly the way a nu index would transform, L nu tau, F tau. When both indices are present, that's it, very simple rule. If you had an object with more indices, you could have any number of indices, the rule would be the same for every index you transform the same way. All right, so that's the rule for transformation of tensors. And now let's try it out. Let's see if we can figure out what the primed tensor is. Let's see if we can discover whether or not there is an electric field along the x-axis. Is that what we want? An electric field let's see, we had a particle moving along this axis here. We had a B field coming out along the y-axis. And we're now going to move, so we should see a z component of an electric field. The question is, will we see a z component of electric field? Okay? So let's try it. Let's try to compute the z component of the electric field in the primed reference frame. We can call this E prime or EZ prime. Let's see if we can calculate that. Now, what is it? What is it? EZ is really F naught Z. F naught Z is easy. I'm not going to worry about signs. Signs are too complicated for me to keep track of. It's either plus or minus this, and it's not terribly important right now. F naught Z is the Z component of, or F time, the mixed space-time component, is the electric field, the primed version of this. That's what I would like to compute. Now, let's go up to this equation and compute it. What do we know, incidentally? We know something about the unprimed tensor. What do we know about the unprimed tensor? That it's a pure magnetic field along the y-axis, right? It's a pure magnetic field along the y-axis, the unprimed. So we know that on the right-hand side, the F sigma tau has only one component, and what is it? It's Fxz. Fxz is what corresponds to By. Fxz is By. So on the right-hand side, there will be an Fxz. There will be two L's. And let's now match indices. Notice this mu index here matches the mu index up here. So we're looking for f naught z. There had better be a naught index up here. What about nu? Nu is associated with the second index here, and that's z. So there has to be a z up here. What about the lower indices, sigma and tau? Well, those have to match the indices over here. So that means that this one is x and this one is z. What happened to the summation that you were supposed to do that's implicit in these formulas here? Well, the summation collapses to a single term for the simple reason that we're assuming that there's only one component of f here, namely the component fxz, and we're only looking for one component on the left-hand side. We're trying to compute a particular component on the left-hand side, and there only is an fxz on the right-hand side. We've assumed only a b component sticking out of the blackboard. All right, so now let's see. Here is our matrix. Let's put these things in. Naught, x, y, z. What is LZZ? That's just 1. Okay? So LZZ is just 1. I don't think I will erase it. I'll just put 1 over here. But what about the mixed component L0x? That's this one over here, naught x. So this one over here has a minus v over square root of 1 minus v squared. So this product is nothing but our old friend v plus or minus, not important, v over square root of 1 minus v squared, and the z goes along for the ride. Now what about fxz? What is that? That's just the magnetic field that we started with, right? So this is just b sub y, the original b sub y. And what's the left-hand side? The left-hand side is the electric field along the z-axis. That's along this axis, the electric field along the z-axis in the moving frame of reference. So in particular, we see that it's not 0. We started with an electric field which was 0 and a magnetic field only along the y-axis. We subjected ourselves to a motion along the x-axis, and what do we discover? That there is, in fact, a z component of the electric field in the new frame of reference. But in the new frame of reference, the electron, or whatever it is not moving. Well, I assumed that. I assumed that I moved fast enough to keep up with the electron, and therefore there's no magnetic force on it. It's at rest in my frame. My frame moving with the electron is at rest, but nevertheless there is a force on it, and the force on it is electric. It's an electric force which is in fact proportional to the velocity. This 1 minus v squared over c squared, this is something very, very close to 1 as long as the velocity is not very large. And so we discover in the moving frame of reference the same effect. The effect which in the stationary frame of reference was due to the magnetic field and the moving charge becomes an electric field acting on a stationary charge. That was the content, if you like, of the first paragraph of Einstein's paper. Of course, no, the content was the question. The rest of the paper was the answer, and this was the answer. Okay, so that, wow, that took 40 minutes. Holy smoke. Well, it took Einstein 10 years. All right, let's come to Maxwell's equations now. Let's come to Maxwell's equations. I am not going to derive them today from an action principle. If we went back to our standard methodology, usually we know what the answer for the equations of motion is, and then we look for an action principle to describe it. We could go the other way, and next week I will go the other way and start with the basic action principle and derive the equations of motion of the electromagnetic field.
That's what you already,
What's that?
isn't that what you already did?
No.
Oh, you're talking about.
No. We're talking about the field equations, not the equations for the charged particle. Okay. There are two kinds of Maxwell. How many Maxwell equations are there altogether? I will tell you the answer. Don't try to figure out that. 8. But they come in combinations. Vector notation converts them into 4. 8? 1, 2, 3, 4, 5, 6, 7, 8. Yes. 8 equations. Half of them, 4 of them, come for free. They come for free. They are consequences of the definitions of the electric and magnetic fields in terms of the vector potential. In other words, half of the equations are simply identities that follow from these equations together with some identities, some vector identities. Identities, you know what an identity is? An identity is a mathematical fact which just follows basically from a definition. But sometimes, even though they just follow from a definition, sometimes they're, they're a little bit non-obvious. Okay, so let me start with 2 basic identities. The first identity involves the divergence of a curl. A now does not have to be the vector potential. A stands for any 3 vector. Only the 3 components for the moment. A stands for a 3 vector. And del cross A is the curl of a certain 3 vector which has been called A. As I said, A could be any 3 vector field. It has to be a field because we're going to differentiate it, but it could be any 3 vector field, whatever. Doesn't have to be the vector potential. Does anybody here not know the definition of the curl? I'm going to assume everybody knows the definition of curl, divergence, and gradient. All right, so the first identity is, what is the nature of this object? What's the nature of a curl? The nature of a curl is it's another vector. It's another vector field. All right, a curl is a vector field, and as such, it has a divergence, del dot. Maybe I should put over here the definition of curl and divergence, just since we'll use them. The curl of a vector can be specified by its components. For example, the x component of the curl of A is by definition dy az minus dz ay. And you cycle through going from one to the next. You let x go to y and y go to z. You can work out the other 2 components. Well, I'm not going to spell them out. You just cycle. Let x go to y, let y go to z, let z go to x, and cycle through them. And you can write out the other 2 components of the curl. Definition of the curl. Divergence of a vector, any vector now, del dot A, for any vector, is a scalar quantity, and it's given by derivative with respect to x of the x component, plus derivative with respect to y of the y component, plus derivative with respect to z of the z component. And the last concept is the gradient of a scalar, which you know very well. I'm just writing them out so that we'll have them. The gradient of a scalar is a vector, and it's a vector whose components, for example, whose x component is just derivative of s with respect to x, and likewise for y and z. All right, so here's the identities. The first identity is the divergence of a curl is always 0. Now, how do you prove that? You prove it just by writing out the whole damn thing. Does anybody want to see it? No, nobody wants to see it, right? No, no. You just literally write out the components of del cross A and then differentiate them according to the rule for a divergence, and you will find out that there's a whole bunch of cancellations. Typically, the terms will involve something like derivative with respect to x times the derivative with respect to y, it's d by dx, d by dy of some a something, minus the derivatives, the same derivatives in the opposite order, and you'll say that that's 0. So just a simple identity. Divergence of any curl is equal to 0. And the other identity is that the curl of any gradient is 0. Given any gradient, the curl of del S, this is a vector, del S is a vector. Let's put some signs here to indicate that they're 3 vectors. S is not a 3 vector, it's just a scalar. The curl of a gradient is also always 0. In particular, I emphasize this is not a statement about any particular vector field, like the vector potential. It's an identity that's true for any vector field, as long as it's differentiable and nicely, smoothly behaved so that you can do the derivatives. Okay, these 2 identities are enough to prove 2 or half of Maxwell's equations without doing anything else. In other words, they follow as definitions, or they follow from definitions. Let's begin with the magnetic field, which is the curl of A. And let's take the divergence of the magnetic field. Let's take the divergence of the magnetic field, del dot B. That's the source of the magnetic field in the sense that divergence, the outgoingness of the field, the tendency of the field to spread out from a point. Del dot B is equal to del dot curl of A from the simple fact, or from the simple definition of the magnetic field as the curl of the vector potential. All right, but the divergence of any curl is automatically 0. So without any further work, no dynamics, no just pure definition or pure kinematics, if you like, the divergence of the magnetic field is 0. What is, just to get ahead of ourselves for a moment, what is the divergence of the electric field? Charge density, electric charge density. In particular, a point charge has a divergence, a spread of the electric field coming out. Among other things, this would say, if it could be trusted, that there cannot be magnetic charges. The magnetic field has no divergence, and so if we saw a configuration with a magnetic field coming out of a point, like out of a magnetic monopole, if there was such a thing, then we would say something's wrong with this equation. If there's something wrong with this equation, there must be something wrong with this definition. So from a simplistic and a straightforward point of view, this equation says there are no magnetic charges. Now, we're going to have to come back at some point and understand there are ways around this, but simplistically, or simply, this is the statement that there are no sources of magnetic field. Now, there's another equation, one of them, this is one of Maxwell's equations. There's another one which also follows for free. Let's go back to the definition that the electric field let's write it over here. Let me just write this as electric field is equal to time derivative of the vector potential, indicate it that way, or, well, maybe I'll just write it as d by dt. d by dt of A minus, now, derivative of A naught with respect to xn, that is just equal to the gradient of A naught. From the three-dimensional point of view, just space, the time component of A can be thought of as a scalar. It's not a scalar from the point of four-dimensional vector spaces, but it is a scalar from the point of view of three dimensions. The vector whose components are derivative of A naught can just be thought of as the gradient of A naught. So we have the electric field, two terms in it. One is the time derivative of the space component of the vector potential, and the other is the gradient of the time component. Okay, now let's let's consider the curl of the electric field. The curl of the electric field is, first of all, the curl of the time derivative of the vector potential. That's the first term. That also happens to be the time derivative of the curl of A. Why is that? Because you can interchange derivatives. When I take a derivative to make a curl out of this, I can interchange the space derivative with a time derivative and pull a time derivative on the outside. So the curl of the time derivative of A is the time derivative of the curl of A, number one. Over here, then we have minus the curl of the gradient of A naught. The curl of any gradient is equal to 0. So we get nothing from here. If I compute the curl of E, I get nothing from here and just the time derivative of the curl of A. But what's the curl of A? The curl of A is just the magnetic field. So here's another Maxwell equation. Curl of the electric field, let's write it as minus the time derivative of the magnetic field is equal to 0. Those are the two Maxwell equations that, as I said, follow from the fact that the electric and magnetic field are defined in terms of the vector potential. There are two more Maxwell equations. Well, how many equations is each? Really, how many equations are here? Well, this is a vector equation. It has three components. So, you know, this is really three independent equations, and this is a fourth one. So this stands for four independent equations. But of course, if we think of them in vector notation, this is one equation, which is a scalar equation, and one more, which is a vector equation. These are, I'm not sure if they have names or not. This is one half of the Maxwell equations. The other half of the Maxwell equations I'll write down over here. And this half is the half that you derive from the action principle. It's the half that is dynamical. It's the half that is not defined in terms of, is not purely definition. It could be different. If I chose a different action, then I could make the second half of the Maxwell equations be different. But the Maxwell equations, as Maxwell knew them, was entirely analogous to these two, basically with the electric and the magnetic field interchanged, but not quite. So let's write down the other two equations. One of them involves the divergence of the electric field. All right, so we know what the divergence of the electric field is. It's called the charge density. We're going to spend some time in a few minutes talking about what charge density and current are. But for the moment, I'm just writing down the equations formally. The right-hand side is the charge density, which means the amount of charge per unit volume, or the charge in a small volume of space divided by the small volume of space. All right. That's what's on the right-hand side here. And the other equation looks a lot like this one with E and B interchange, but not quite. It's del cross B plus dE by dt. And what is it equal to? The current density. I will tell you in a moment. So far, we're just going to give it a name. We're going to give it a name, and that's all. We're going to call it J. Now, what kind of quantity is J? Well, the left-hand side is a 3-vector. Electric field is a 3-vector. Its time derivative is a 3-vector. The curl of a 3-vector is also a 3-vector. So J is a 3-vector. And rho is a 3-dimensional scalar. Now, they're not in 4-vector language, more complicated. In 4-vector language, we will discover that the 3 components of J and the rho together form a 4-vector. There are 4 components, 3 components of J and 1 component of rho.
Give a name to J.
J is called the current density.
Current density.
The electric current density, right. And rho is called the charge density. Charge density and current density. So let's talk about them, and let me explain what they are, the J's and rhos. Oh, cool. This is rho, the thing in here. But, somebody's teaching quantum mechanics. Next quarter, I have a crazy teaching assignment. Steve Schenker and I are volunteered to do something which I know is going to be incredibly frustrating, to teach quantum mechanics in the mathematics department.
Frustrating for whom?
Well, possibly for the poor sucker physics department students who have to have a mathematician come and teach statistical mechanics. No, I think it'll be fun, actually. Someday I'll tell you why we decided to do this. This is not an undergraduate course. It's mainly the faculty who wanted to learn quantum mechanics. They heard that they cannot understand. Ed Witten told them they have to understand quantum field theory if they want to understand basic modern mathematics. And they believed him, so they tried to understand quantum field theory and found out they couldn't understand it. And so they said, well, the reason we can't understand it is because we don't know anything about quantum mechanics, so please help us, teach us quantum mechanics. Why am I getting into this? Forget it. But yeah, okay. Charge density and current density, what are they? So let me explain exactly what they are. First of all, charge density is exactly what it sounds like. You take a region of space, and I'm going to draw some pictures. Here is time, and the other 2 directions are space. Now the problem here is, of course, there are 3 directions of space, and it's going to be a little hard for us to, I'm not going to try to draw four-dimensional space-time on the blackboard. So we'll have to imagine that these two directions are stand-in for 3 dimensions of space and 1 direction of time. All right, we take a little cell in space. I'll draw it as a little square here, but of course it's a cube. It's not a square, it's a cube. It's a cube because it has 3 dimensions, and therefore it's a little volume element, a small volume element. We imagine charged particles. Charged particles have world lines, so let's draw some world lines. And let's imagine that the space and time are filled with a kind of a bundle of charged particles moving, sort of flowing, a fluid of them. Those are the world lines. And think of the world lines that pass through. Here they are. They're passing through this little cube. Now, what does it mean? That means that at an instant, here's an instant, at an instant, the particles which pass through that cube are simply the particles that are in the cube at that period, at that instant of time. All the particles, the charged particles, they could be electrons, for example. We take all the electrons that are in there, we count up all their charges, and we think of it as the total charge passing through that little volume of space. Passing through in the sense they were in the past, then they were in the future, but at the instant that we drew that little volume element, they were in the volume element. And so you can think of them as passing through the volume element. The total charge in that volume element divided by the volume element is the charge per unit volume, and it's rho. Rho is equal, let's call it the charge within the volume delta V. Delta Q over delta V in the limit that the volume element goes to 0. I don't have to spell that out. Infinitesimal volume element, infinitesimal charge in there. That ratio, charge per unit volume, is called the charge density. And it is literally the amount of charge per unit volume. Now, what about the current density? The current density is simply this thing turned on its side. Now, here is where we get into a little bit of problem. The vertical axis here is time. The horizontal axis, or the two horizontal. Let's get this right. There's a time axis, and right there. That's it. All right. Now, this is the x-axis. This is the x-axis. I guess this here stands for the y and the z-axes. Since I can't draw them, I'll just call them the y and z-axis. All right, so think of a little cell here in space and time which is perpendicular to the x-axis. That means it's a little cube in space and time. In space-time, it's a cube. It has an edge along the time axis, and it has 2 edges along the y and z axis. Let me take it out and put it over here and draw a pure space diagram, x, y, and z. This edge over here really stands for a 2-dimensional square, the y and z square. And so it's a little square in the, yeah, that's okay. It's a little square in the yz plane. We can ask, how much charge, think of it as a window. Think of it as a window. There's a little window over there. If I'll get into big trouble if I draw a window on the wall here. Okay, I won't. All right, here's the window, this thing over here. That's a window. And that window is along the YZ axis. It's what's that? Yeah. Wait a minute. I guess the window here is on the ceiling. Sorry, the window here is on the ceiling. Yeah, the problem is there's just not enough axes in the world to draw. In any case, there's a window. The window in this case is perpendicular to the x-axis. So if the x-axis is that way, yeah, if the x-axis is that way, the window is in the yz plane. It's like that. And now I ask the question, how much charge passes through that window per unit time? The amount of charge that passes through a small window per unit time. In other words, it's the charge passing through a little cell per unit space per unit time, per unit area per unit time. The amount of charge passing through a unit area in a unit time, or per unit area per unit time. That's the precise analog of turning this on its side. This cell was perpendicular to time. This cell is purely spatial, but it's perpendicular to the x-axis. Sorry, it has a time component and a y and a z component, no x component. So it's like turning it on its side. That's called J. J sub x, to define J sub x, you take a window perpendicular to the x-axis. Perpendicular to the x-axis, you ask how much charge is flowing through it from the negative x side to the positive x side. How much charge flows through it per unit time? So Jx is the charge per unit area per unit time. Volume, area times time. And this area here is an area perpendicular to the x-axis. In other words, it's a yz area, but perpendicular to the x-axis. That's Jx. Okay. What about Jy and Jz? Jy and Jz are the same thing. The amount of charge per unit area per unit time passing through a window perpendicular either to the y direction or the z direction. So there's J sub z, J sub y, and J sub z. The formula is the same, delta Q over delta A, delta T, except delta A is a little window perpendicular to either the y or the z axis. That's the definition of J. And in fact, Jx, Jy, Jz, and rho form a complex of things which in fact are a 4-vector. We'll see why I say they're a 4-vector soon enough, but they are a 4-vector. And they enter into Maxwell's equations. Where were Maxwell's equations? Did we erase Maxwell's equations? Oh, here they are. Here they are. Yeah. And that's what's here. The J's are kind of flow of charge. They represent the flow of charge from one place to another, across these windows or through the windows. All right, so the x component of del cross B plus the time derivative of the x component of E is equal to the flow of charge through the x window. There's one more thing about the charge, about the density and current vector, which is important. It actually can be derived from Maxwell's equations. Let's see. Yeah, we can derive them from Maxwell's equations. I won't, but I'll let you do it. You can derive it from Maxwell's equations, but it's really just charge conservation. So let's talk about charge conservation. Yes. In fact, let's take a break for 5 minutes. Ask me the question, but let's take a break for 5 minutes, during which I'm going to take my jacket off.
So basically these four numbers are just the components in the, one is flow in the time direction and the other one is flow in the
Right.
x, y, and z direction.
Right.
The other, right? Is that
You
what
can,
it's-
that's the way to think about it. Yep. Right. So you can think of a spatial volume as a kind of window perpendicular to the t-axis. And if you think about it that way, then uniformity, 4 definitions.
Does the eta function come into play eventually?
in this scenario?
The eta.
Yeah.
You mean
Time component is negative.
yeah, I think you're asking a sensible question, but I would rephrase it. I would ask whether the rho and j are a covariant or a contravariant vector, 4-vector, and we'll come to that. We'll see that as defined, they form the components of a contravariant vector, upper index. In other words, and we'll see why this is soon enough. We'll see that the complex rho, jx, jy, and jz can be thought of as the components of a 4-vector called j mu with an upper index. But we'll come to why that's true as soon as we study the relativistic formulation of the Maxwell equations. Okay, let's take a 2-minute break. I'm happy to answer questions, but I want to take a break from lecturing for a few minutes, for a couple of minutes.
I have a question. My son was watching you on TV, and he asked me a question about something that you said, and I didn't know the answer. So maybe you can tell me, and I'll tell him.
Yeah.
He was watching that show where you were talking about black holes and the different point of view of somebody falling in versus the person watching.
Right.
And from what you described, the person that's outside the black hole sees the person falling in and slowing down and eventually stopping. So what he asked me is, like, if it eventually stops, wouldn't you see around the black hole basically everything that's ever fallen onto it, and you wouldn't see a black hole at all, but just a bunch of litter?
Classically, the answer is yes. That what you would see, all the stuff that falls onto the black hole forms kind of sedimentary layers, which just asymptotically, slowly gravitate to the horizon. Quantum mechanically, well, it also slows down. It also slows down, which means that the radiation coming, you know, if I were this infalling person and I was sending out messages, let's suppose I was sending out messages at some frequency. So, as I would approach the horizon, I would send out the messages in a way that sounds to me normal, okay? But to you far away, it would be redshifted. Redshifted means that the frequency would get lower and lower and lower. And if the frequency of the sound that I was making was a finite frequency, there basically would be a last wave that I would send out before, before the end of the message. Now, I could send out more waves if I would increase the frequency. I'll make it higher and higher. But for any given frequency, there would basically be a last bit of the message that I could send out. So for any finite thing falling in with a finite frequency, with a finite amount of energy available to send out photons and so forth, it will slow down, get redder and redder and redder. My flashlight that I send out with optical radiation will look to you as I fall in as infrared. I fall in a little further, it starts to look like microwaves coming out. Not look like, it's microwaves coming out. Not to me. I'm sending out perfectly good flashlight light. You're seeing infrared, microwave, radio wave, longer and longer wavelength radio waves. The photons coming out carry less and less energy, and so in effect it turns black. It does turn black.
Is this asymptotically approaching the event horizon?
Yeah.
Yeah.
Quantum mechanically, it's a little more complicated because the event horizon has a temperature. And so this reddened radiation gets mixed up with the Hawking radiation that comes out and becomes indistinguishable from it. So
What would happen when the
wavelength gets shifted to the point where it's exceeding the radius of the observable universe? Does it just disappear?
Clearly it's lost, but it's lost long before that. That's a good question. I mean, it's a good question. Basically, the black hole sends out one photon per transit time across the black hole. Transit time across the black hole, the horizon of the black hole has a certain radius called the Schwarzschild radius. There's a time associated with the transit time across that. You know, just what do? You take r and divide it by c? Yeah, you take r and divide it by c, that gives you a time. And every such time unit, it sends out one photon. Now, that's not a lot of photons. One photon per transit time is a very, very weak radiation. But on top of that, the radiation gets longer and longer wavelength. So that means the black hole, as it radiates, I'm talking about the Hawking radiation now, it sends out longer and longer wavelengths, and one per horizon crossing time, and that really just gets to be negligible from the point of view of anything that we could reasonably measure. It's so yeah, in that sense it gets quite black. Yeah.
Is that rate, one per transit time, the same during the life of the
No.
black hole?
No, the black hole evaporates, the thing shrinks, and so it speeds up in that sense. But
that relationship still holds for
yeah, 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 yeah. Okay. All right, we've defined J, so we know what's on the right-hand side of this equation. Now, it's an interesting exercise. Try to work it out. I think it's almost obvious, but I'm going to let you work it out. From this equation, we could compute, oh, wait, no, I didn't give you the punchline yet. No, go back. Rewind. Conservation of charge. Conservation of charge is what it says it is. The total charge in the universe doesn't change with time. But really, the conservation of charge is a more detailed law than just saying the charge in the universe doesn't change. It says it doesn't change, and it doesn't change in a special way. The special way, the special way is the following. If I take a region of space, first of all, what does the conservation say? Start with a region of space that I'm interested in, and look at the total charge in there. Let's call it Q. Q is a standard terminology for electric charge. Call it Q. Let's suppose after a small amount of time, the charge within this region has changed. Maybe it's decreased a little bit. That means the charge someplace else must have increased. That's conservation of charge. But the conservation of charge wouldn't be very helpful to us if there were no rules about where the charge increased. For example, it would be perfectly consistent with the conservation of charge that every time the charge changed in a box over here, it reappeared instantly at Alpha Centauri. But then from the point of view of our laboratory experiment, it would be tantamount to saying that the conservation of charge would be meaningless unless we could do an experiment that involved out to Alpha Centauri. And if you can do an experiment out to Alpha Centauri, go out to the Coma cluster or wherever you want, conservation wouldn't have much bite if the rule was simply that the quantity, total quantity, doesn't change. The real rule is that the charge within a region can only change if it passes through the walls of that region. In other words, somebody's standing and monitoring the boundaries of this box will, if the charge on the inside changes, it will be due to the fact that they discover charge passing through the walls of the box. Now, the walls of the box are these little windows. So what it says is that changes of charge in the interior of a box must be accompanied by something or other having to do with the current on the boundaries of the box. In other words, a change in charge, let's take this to be a small box, then the charge inside that small box is basically the volume of the small box. I'll take the volume to be 1 so that I don't have to write it over and over again. Let's take the volume to be 1, but think of the volume as small. But in some units where a small volume is just a unit volume, then what is the time derivative of the charge in that box? Well, the charge in that box is just the charge density if I take the volume of the box to be 1. If the volume of the box is 1, charge per unit volume, then rho is just the charge in that box. The time derivative of the charge is just rho dot, the time derivative of rho. What the conservation, or we can call it the local conservation of charge, the idea that charge can't change within a volume unless it's discovered to be passing through the walls, that's called local conservation. Okay? Local conservation says that rho dot must somehow be connected with, which means equal to, something or other about the boundaries of the box. Okay, so supposing rho, let's take the case where it increases. Supposing the charge increases. That must mean there's some net flow of charge coming in. The net flow of charge coming in must be the sum of the charges coming in through this window, plus the charge coming in from this window, plus that window, plus the ones in the front and the back. Okay, so let's consider the charge coming in through this window over here. What is that? That's the value, let's take this to be the x-axis. We'll take that to be the x-axis. The vertical one will be the y-axis. The other one is x, y, z, z-axis. The charge coming through this window over here is proportional to jx. Now, in fact, jx is defined in such a way that it corresponds to the flow from lower values of x to larger values of x. So in particular, the charge coming into here per unit time through this window is actually minus jx, and it's minus jx at that point, or in the neighborhood of that point. So there's some charge flowing in from here, and we can add them all up. Minus jx over here. What about over here? What's the charge flowing in from this side? It's plus jx, but not at the same point. Jx at a somewhat displaced point, displaced along the x-axis. So if I take this contribution and that contribution, it corresponds to a certain derivative of jx, the difference between jx over here and over here, and it is basically the derivative of jx with respect to x. In fact, it's minus the derivative of jx with respect to x. That's the contribution from the two faces which are perpendicular to x. The two faces which are perpendicular to x, the charge per unit time, flowing per unit time, is proportional to minus the derivative of jx with respect to x. What about the charge flowing into the box through the y faces, through the faces perpendicular to the y-axis? Same thing, minus the derivative of jy with respect to y. In other words, some charge flowing in here, some charge flowing in here. Because of the opposite sense of direction, it's a difference, minus jy with respect to y. And finally, minus the derivative of jz with respect to z. This is the net charge per unit time flowing into the box by flowing through these three kinds of windows. This must be equal to the time rate of change of the charge in the box. So we now have an equation that rho dot is equal to minus, and what is this? This is the divergence of J. del dot J, or rho dot plus del dot J is equal to 0. That equation is a local point, sort of neighborhood by neighborhood expression of the conservation of charge. If it's true, then the charge within any small region will only change due to the flow of charge out of that region, the flow of charge through the walls of the region. Okay. All right, so that's the idea of, this equation is known as the continuity equation. Continuity. I don't like thinking of it as a continuity equation because continuity sounds like something is necessarily continuous, which it's not. I like to call it local conservation. In other words, conservation, but a strong form of conservation which does not allow a charge to disappear at one place and reappear at another place unless in between there's a flow of charge, a current. Okay, so this is the continuity equation, and it's another equation that has to be added to these, but in fact it really doesn't have to be added to these. It's a consequence of these equations. So I suggest to you the following exercise. Here we have an expression for rho. Here we have an expression for J. You can take the time derivative of the left-hand side, and it will give you rho dot. You can take the divergence of the right-hand side, and it will give you divergence of J. See if you can prove that as an identity, that rho dot plus del dot J is equal to 0. In other words, that Maxwell's equations require the charge to be conserved. It's such an important thing that I'm sort of tempted to see if I can do it on the blackboard. It is really central. It's really central. Charge conservation is not an option that it follows from the Maxwell equations. I'm going to let you do it. It's fun. It's a little bit of an exercise. It uses a couple of identities. And, you know, it's truly central to the whole game. Okay, so now we have Maxwell's equations, and the real question that I want to address is, can we express all of these equations in a relativistic notation which makes it clear that the collection of equations is invariant under Lorentz transformations? In other words, can we express them as tensor equations? Equations with indices, upstairs, downstairs, with the rules of indexology.
Question?
Yes, sir.
We didn't really show those last two equations, how they came to be, did we?
Which one?
The second set of the hard ones.
No, we haven't come to these yet. We have not.
Okay.
We have not. No, exactly.
But we're moving forward.
No, that's right. Well, this is the target. This is the target. This is Maxwell's, let's see, this and this were known to Faraday. Faraday also knew that del cross B equals J, but he didn't have it worked out in the case where there was time dependence. This term here was invented by Maxwell. Without this term, you would not discover, in fact, you would discover that charge conservation is false. This term is essential to prove that rho dot plus del dot J is equal to 0. So in fact, what Maxwell did is he knew about charge conservation, so did Faraday. They knew about charge conservation, they knew about the continuity equation, and Maxwell realized that he has to put this term in order for charge to be conserved. That it wouldn't work unless you added this term over here. So that's a nice exercise to work out. Okay, let's see what we can do about making these equations relativistically invariant. In other words, some just relativistic notation. Well, This one over here is pretty clear. It's pretty obvious. Let's rewrite it in a form that is easy to see. Rho dot is d by dt of, let's call it rho. It is rho. What about this? This one is plus d by dx of jx plus d by dt, or sorry, d by dy of jy plus d by dz of jz. Now, so far, I've not been thinking about four-vector notation and so forth. We've been thinking three-dimensionally. So from the three-dimensional point of view, there is no difference between an upstairs index and a downstairs index. But when we look at this equation, it becomes natural to think of it in a notation which is sort of manifestly Lorentz invariant. First of all, differentiating with respect to an xm, that's a downstairs index. If we write the index upstairs, then this is part of a scalar. Let's say it more completely. Let's define rho to be the time component of j. In other words, take jx, jy, and jz, put them together with rho, jx, jy, and jz. I'm putting the index here upstairs, but it doesn't matter because three-dimensional indices doesn't matter whether you put them upstairs or downstairs. Put them together and call the whole complex of four objects J mu with an upstairs index. Then this equation has the form of a four-dimensional relativistically invariant equation dj mu by dx mu summed over mu, Einstein's summation in the convention, equals 0. So it's natural, therefore, to think of rho together with j as the components of a four-vector. In fact, it's not hard to prove that they really do transform as the components of a four-vector. Let's not try to do that at the moment. Let's just make use of our notation to take it as a very strong suggestion that the components of rho and j form a single complex. Now, of course, they do. They were defined pretty much in the same way. You took windows in various directions in space and time and asked about the charge passing through those windows. So it's a rather symmetric thing with respect to space and time. And in fact, that symmetry is just the statement that the complex rho j form a four-vector.
Question.
Yeah.
Is there some trick that I missed when the total derivative of rho with respect to t became a partial derivative?
Oh, no, it is partial derivative. It was always partial derivative. It was always partial derivative. Why? What does it mean? It means you stand at a point in space, a little box, and you ask how much the charge inside that region changes. Now, we're not moving the box from place to place. We're keeping the box fixed. That means we're differentiating with respect to time, keeping x, y, and z fixed. All right? We're looking at a particular box. We're not moving it. And we're saying, what's the rate of change of charge in that box? That's a partial derivative because it's asking how the charge density changes if you vary time, not varying x, y, or z.
Okay, so rho dot could signify partial derivative.
Yeah, rho dot, here rho dot meant partial derivative. Yeah, partial derivative, right. We're not following some trajectory, we're just looking at a fixed box. So that's right, rho dot just meant literally partial derivative with respect to time. That's a good point. Okay, and then the rest of them are also partial derivatives. So now we have the elements necessary to, we know that E and B form a antisymmetric tensor with two indices. J and rho form a 4 vector, in other words, a tensor with one index. And here's a set of here are a set of 4 equations, and the question is, can we express them in a way which is invariant under Lorentz transformations? Let's begin with the left side, not the left side, sorry. Let's begin with the 2 equations in this box, the equations that were for free, the equations that were just a consequence of the definitions of B and E in terms of the vector potential. What are they? They're some kind of derivative. Each one of these equations has a derivative acting on a component of f. And the result is equal to 0. How many such equations are there? There are 4 such equations. Here's 1, and there are 3 more here, 3 because it's a, right. So there are 4 such equations. And I will just show you how to write them out in tensor notation, and then we can check. We can check them one by one and see that they're the same set of equations. All right. Here it is. You know, there are some tricks to doing it, but the answer is more interesting than the tricks, or the answer, the fact that it's covariant. All right, so let me write it out for you what it is. It's d sigma. Now, sigma can be any one of 4 t, x, y, or z, or 0, 1, 2, or 3. F nu tau plus d nu. I'll tell you how you get this in a moment. D nu tau sigma plus d tau f. Now, let's see, it's tau, so it's got to be nu and sigma, and it must be sigma nu equals 0. You take any 3 of these components, sigma, nu, and tau, for any combination of sigma, nu, and tau, 1, 2, 3, 2, 3, 1, whatever, this is equal to 0. That's equivalent to these equations. Let's check. Let's just check. The way to do this is just to go through them and check. In particular, let's take the case, let's see, let's take the case first where all 3 indices, sigma, nu, and tau, are space components. Okay? Let's see what this says if sigma, nu, and tau are space components. So this is d, well, I won't rewrite it. I'm getting a little tired, but let's go through it. Yeah. Notice, let's see. Let's take sigma equals x, nu equals y, and tau equals z. Let's try that combination and see what we get. Then, this is derivative with respect to x. Now, this is f nu tau, so that's fyz. Fyz is what? It's a component of the magnetic field. Which component? Good. Bx. Okay. How about this one over here? Now, nu is equal to y. So this is plus derivative with respect to y. Tau and sigma, what are tau and sigma? Z and x. So what kind of b is that? By. We have to check, you have to check the sign. The only thing that could go wrong is the sign. And the last one, tau is equal to z. And sigma and nu are x and y, so this is bz. And that's equal to 0. That's simply del dot b is equal to 0. Okay? So if we take all three of these to be different components and pure space-like, sigma, nu, and tau, we just get del dot b equals 0. We get exactly the same thing, incidentally, if we took nu to be x, and sigma to be y. Wouldn't change. You get the same thing. Okay. Let's try another one. Let's take one of the components to be a time component. Which one? Which do you have a preference for which one is time? Tau. Oh, good. Tau is time. Yeah, tau is time. And let's take sigma and nu to be y and x again. So let's see what this says. Okay, d sigma, that's derivative with respect to y of nu tau. Now what's f nu tau? One leg in time and one leg in space. That's an electric field. The electric field are the mixed space-time components of f. All right, so this, well, let's not try to keep track of the signs. It's a little too tricky to keep track of the signs. Let's just be a little loose with the signs now. F nu tau is E sub x. So this is derivative with respect to y of E sub x with a plus or minus sign that is a little too hard to keep track of in real time on the blackboard. What about this one? This is plus or minus derivative with respect to x of f sigma tau, that's E sub y, and no doubt there is a minus sign between them. So what is this a component of? What is this thing here? That's a piece of the curl. It's a component of the curl of E. Which one haven't I kept track of yet? This one? Okay, so this one is plus derivative with respect to t of f sigma nu, that's the magnetic field in the z direction. F x y is the z component of the magnetic field equals 0. And again, there's some sign there that I haven't kept track of, but that's just that the curl of E minus the time derivative of B is equal to 0. You can go through all of these equations. You can just see there are some repetitions. In general, it doesn't matter which way you set sigma nu and tau, x, y, t, or t, y, x, to get the same equation. You'll just find that these equations, all of them, for all possible sigma nu and tau, either just give you 0. There are times when you just get 0. In particular, if any two of the components are the same, you'll get 0 every single time. And if they're not the same, you'll get either this equation or this equation. So the first equation here can be represented in a completely relativistically invariant tensor notation. This is a tensor with three components, or three indices, sigma, tau, and nu. And this is true. You can check this another way. You can remember that f is the derivative of a nu with respect to x tau minus the derivative of a tau with respect to x nu. That's this one. And then you have another one over here, and another one over here. And you can simply work them all out, and you will discover term by term they cancel. They just cancel among themselves, and you get 0. So these equations here, the ones which come for free, the ones which just are determined by the fact that f is defined in terms of the vector potential, they are equivalent to this tensor equation. It's completely Lorentz invariant. You can check that. You can see how it transforms. And this equation, or this complex of equations, has a name. The name is called the Bianchi identity. Or it's a special case of an identity called the Bianchi identity. Giorgio, is there an H in that?
Yes.
Yes. The Bianchi identity. There's a similar identity in general relativity. It has a certain geometric meaning, and the geometric meaning is interesting, but it's not for us tonight. What does it express? Again, one of the things it expresses is the fact that the magnetic field has no divergence, so there's no charge densities, no magnetic charge densities. But if there are no magnetic charge densities, there are no magnetic currents. You might have thought that by analogy with this equation, you could put a magnetic charge density here, the analog of an electric charge density, and a magnetic current over here. What we're finding is that the Bianchi identity is the statement that there are no magnetic charge densities or magnetic currents. Right. Next time, we will come to these equations. These are the equations which are derived from an action principle. These, as I said, are just identities. You get them for free. These are the ones that are derived from the action principle, and we'll do that next time. Okay, I think we're finished for tonight. Any questions? Yeah.
So that the capital F matrix essentially has 6 independent entries.
Yeah.
And
3 electric and 3 magnetic fields.
right, and that's 64 different equations.
Yeah, there's not that many there.
And we end up getting 4 pieces of interesting information out of it. Is there any?
Yeah, there is, but I'm going to let you do it.
Okay.
You'll just discover that the 1, 2, 3, that if any 2 of them are repeated, you get 0. In other words, the x, y, y component is 0. And you'll discover that the 1, 2, 3 component piece of the equation is the same as the 2, 3, 1, is the same as so there's only a handful of independent ones, and that you can check. So, as you said, it looks like there's what 64 equations here, 4 times 4 times 4, but there aren't. There are not. There are really only 4.
How many of them?
There are only 4.
Pardon?
There are only 4 really, namely these.
Right, I understand, but
Yeah.
there are literally 64.
Yeah, literally 64.
Most of them go away.
Right. Well, it's not that a good number of them go away, and a good number of them are just repetitions of other ones. Right. That's true. Yeah. So that's yeah.
If your charge and current are 0, then you have the duality.
If what?
If charge and current are gone, the duality between E and B. So I'm confused when you have your space, your E's are your time space and your B's are your space. What's the meaning of that in light of duality?
Yeah.
What's special about E that it's time and space?
In the end, as far as we think we understand things, there is no difference. I mean, that is to say, if there was such a thing as magnetic charge density, we would put it in on the right. Let's call this electric charge, electric current, magnetic charge, magnetic current. I can't remember. Yeah, I think I'm not sure about the sign of this one. Maybe a minus sign. I can't remember. They're completely parallel or invariant with not with respect to changing E to B and B to E. That doesn't quite work. Why not? Because of this minus sign here and a plus sign here. You think about it a little bit differently. You make a plane whose axes are E and B. Okay, now interchanging E and B would be reflecting E into B and B into E. That's not what you do. What you do is you rotate the diagram by 90 degrees. E goes to B, but B goes to minus E. That's the duality. E goes to B, B goes to minus E, and either electric charge goes to magnetic charge or electric charge goes to minus magnetic charge. So there are many, many ways of expressing this duality. But if you go back and you say that E and B really came from a vector potential, then at least at a naive level, it would say that the magnetic charge and current are zero. And, so.
It seems so clean and elegant and everything, the way that E and B interchange and all fits with relativity. Mm-hmm. It almost seems meaningless to talk about a magnetic monopole given that. What I mean, you have to change what you mean by magnetic field almost, or something. You know what I mean?
Yeah, of course I know what you mean. We will come back to magnetic monopoles. I will try to cover magnetic monopoles this quarter and discuss how they fit into this picture. Now, of course, it's an interesting fact that nobody's ever discovered a magnetic monopole, but we'll come back to that. Let's not push it tonight. I'm tired. Okay, good.
For more, please visit us at stanford.edu.